These are instructions for Lab 6, Geoworld. And if you're a fan of a certain series of books or a series of movies made from those books, I think you'll recognize some of these locations. Make sure you watch the 2 parts of video Plate 3B.6 because that explains isochrons and seafloor spreading and will be important as a background for this lab. Notice that I'm only assigning the pre-lab questions and parts 1 through 3. Parts 4, 5, and 6 are topics we really haven't covered yet, so you don't have to worry about those. So first of all, there's a set of pre-lab questions that I want you to answer, and these really should be review for what you're understanding about plate tectonics by this point. What is a divergent plate boundary? Give a definition. Give a geographic name of an active divergent plate boundary, not just the plate, and I've made this point before. So don't say the African plate, because that's not a boundary. Think about the boundaries around the African plate and then choose one of those and then give that name. That's a plate boundary. How did divergent plate boundaries come into existence? Think about the creation of a new ocean basin. What is a convergent plate boundary? List the 3 subtypes and give examples of them. What's a transform boundary? Give an example. So these are the 3 types of plate boundaries, and by now you should be becoming familiar with those. Now this last question is sort of a new topic. How can the rate of plate movements be determined? And basically we're going to use a very simple equation, the speed or velocity or rate equation, which is distance over time. Let me give you an example of how we're going to use that. Here I've drawn a seafloor spreading system map view looking down, and I've got a key for polarity, so everything in green is normal polarity ocean crust, and everything in white is reverse polarity. This red region right here is where today there's brand new seafloor being created, and the 2 sides of the boundary are moving as shown by the arrows. Now let's say that I know that this reversal right here recorded in the seafloor occurred 2 million years ago. Well, remember that the isochrons are symmetrical about the ridge axis, so there must also be a 2 million year isochron mark over here. Now, if I measure the distance between those 2 points, that's how far this seafloor has spread in 2 million years. So I get the distance, and I divide the distance by the time, and I get the rate. Speed equals distance over time. In this case, it's 52 kilometers over 2 million years. And then we're going to divide, and we get 26 kilometers per million year. Now, I'm going to show you a little trick that I don't think anyone uses except geologists. And this is actually on question 6 as you move along through this exercise, but I'm showing it to you here. If you find a rate in kilometers per million years, the zeros will cancel out on the top and the bottom so that you can use that exact same number with the units of millimeters per year. So if something's moving at 27 kilometers per million year, it's moving at 27 millimeters a year. Just happens to work that way. So if we are moving 26 kilometers every million years, we are moving 26 millimeters a year, or what I prefer is centimeters per year, 2.6 centimeters per year. And 2.6 centimeters is maybe about that much, and that's a decent, reasonable rate for seafloor spreading. So back to the lab. Here we are on the 2nd page of the lab after you've done the pre-lab, and you'll just want to read this upper part because it tells you about the activity. Basically, we're going to look at this place called Geoworld, and the magnetic reversal timescale on Geoworld is given here. It might take you a moment to wrap your head around this diagram. So we're looking at a map, and here is a continent called the Frodo continent, and there's some mountains in it. And then there's an ocean called the Elrond Sea, and I put that in blue to kind of emphasize that this is a seafloor. And what you're seeing in the striped pattern are the isochrons from seafloor spreading. We then have another continent called the Bilbo continent. It has another set of mountains in it. And then we have an ocean called the Aragorn Ocean. And the Aragorn Ocean has some different kinds of islands in it, the Gandalf Islands, the Galadriel Islands, and it also has a trench called the Sorin Trench, which hopefully you know now, trenches are associated with subduction zones. The first question says, observe the magnetic anomaly patterns on the map of Geoworld. Which ocean has a symmetric pattern and which has an asymmetric pattern? So they're asking you to look at the pattern here in the Elrond Sea and see if there's any place that you could divide this that would provide symmetry. So if we look at this large normal polarity location here, then on either side there's a tiny reversal, then a tiny normal, then a big reversal, etc. And so it looks like right down here, this half is the symmetrical image of this half. And then you can see that same pattern repeating throughout the sea. If we look here, I don't see any mirror image anywhere in the pattern. I see a big solid bar, a big white bar, two solid bars close together, a big white area, two solid bars. I don't see any symmetry there. Which ocean has the symmetrical pattern? The Elrond Sea. And which one has the asymmetrical pattern? That would be the Aragorn Ocean. So which one has active seafloor spreading? I'll let you answer that. It now says on the map, highlight the mid-ocean ridge and label it the Hobbit Ridge, and find it by looking for the magnetic anomaly patterns. We're going to say that this is the active ridge system since we saw a symmetric pattern, and we're going to indicate where present-day seafloor spreading is occurring. And so that's probably right in this middle place. And remember, they're all offset by little transforms. And we're going to label it the Hobbit Ridge. It now says in one or two sentences, explain the origin of the striped magnetic anomaly pattern in the Elrond Sea. And I've sort of mentioned it a number of times. It has to do with seafloor spreading. So give an explanation. Don't just write seafloor spreading. Why do we see that pattern in the Elrond Sea? And then it says the pattern can be correlated to the magnetic time scale. And so we could try to figure out when the spreading began in this sea. So here I've put the time scale. And so we need to figure out if this is today, then this very first little reversals here, and then the normal polarities there, and then that larger reversals here. And you can keep going and matching back and back until you come to the point where this particular anomaly is on here. And then you'll know the age when spreading began. Next part is going to ask you to look at the spreading rate from the Hobbit Ridge to the Frodo continent. And this is going to be a half spreading rate. So it's a little bit different than what I showed you. This is only going to give you 1/2 of the spreading. And so you're going to go from the Hobbit Ridge to the Frodo continent. You're going to use the scale here to measure it. And you can do it from here or here. It's up to you. And you're going to take this distance, right? You're going to divide it by the time. And you're going to find out the half spreading rate. And then to get the full spreading rate, you're going to double that. So part 2, it asks you to highlight the plate boundaries that are there. There are 2, and we already highlighted one of them. It asks you for an example of each of these plate boundaries in Geoworld. So look on that map, find a divergent plate boundary and give it name. Find a convergent plate boundary and a transform boundary. And this one you might have to give a name to. How many lithospheric plates are there in all? I'm going to leave that to you. Now, the last part, last question is right here. And this one's a little tricky because you've never done a cross section before. So I'm going to do it for you mostly, and then you're going to finish it up. So what a cross section means is they've got this line A prime, and they want to take a slice through the earth right there, and they want to show you what that slice looks down here. So to start with, we can see that there's several things above sea level and several things below sea level. We have several coastlines. So we might as well put in an arbitrary line for sea level. We don't have any elevation values, so it doesn't really matter. This is all sort of relative. Here we have a coastline crossing our A prime line right here. So down in our cross section, we can put the Frodo continent with the Misty Mountains, and then there's the coast. And we'll stop right there. We won't go further until we think about what else is on the diagram. Now here we have another coastline, and here we have another coastline. And these are between the Rivendell Mountains on the Bilbo continent. So we can put in the Bilbo continent with some mountains. We also have the Galadriel Islands popping up above sea level on the left side of the diagram, so we can put that in there. And these are active volcanoes, so I put a little active smoke coming out of it. Now we have to think about what's going to go on in the oceans. Well, remember we have a ridge here, and it crosses the AA prime line right here. So down below, we need to put in the seafloor spreading ridge, and remember it's elevated right where the spreading occurs. Let's put in some more parts of this diagram so we can think about lithosphere and a asthenosphere. Now, what about on the left side of the diagram? Well, we have a trench, and a trench means that there's subduction going on. And it turns out that the triangles, they're always on the side of the subduction zone that is the upper plate. And what that means is that the plate on the right is going down below the plate on the left. So that's our whole diagram. That's our cross section. Now it says draw the entire thickness of the lithosphere and part of the asthenosphere and label crust mantle, lithosphere, and asthenosphere. So I leave that to you. I did not separate crust in this diagram, so you're going to have to figure out how to do that. I will show you with arrows, though, which direction everything's moving to make sure you're clear. All right, as I said, parts 4, 5, and 6 are optional, but if you're anxious and excited about this, go for it. We'll probably talk about these later in the week when you get the lab back. All right, good luck.